Hello everybody, nice to meet you. My name is Stefan Schiessl. I'm from Fraunhofer IVB. As my previous speaker Cornelia Stramm, I'm working in the Department for Materials Development, and I'm there since August 2019, so since 5 years, and I'm writing my PhD thesis on the development of nanocomposite barrier lacquers for oxygen, water vapor, helium and hydrogen. And today I have the honor to present paper-based packaging, and the paper-based packaging is very important in especially German or in the Middle European region, because there is a high demand for paper-based packaging because of several reasons. First of all, it is assumed by the customer to be green. There are regulatory topics that request for paper-based packaging, especially when we think about the single-use plastic derivative, where it is not allowed to use single-use plastics anymore, and their paper would be one possible replacement. Especially for the recycling topic, there is an established recycling stream for paper-based packaging, and this recycling stream we will use and we can deliver with the paper-based packaging. Next slide. So there are several advantages and disadvantages when we think about paper-based packaging. First, the advantages: paper has a very high mechanical strength. It can be folded. It has light protection, so it's an opaque material. But there are also some disadvantages, like for example the resistance against water. Paper has a certain dependency on the environmental conditions, so if there is a high humidity, the mechanical strength of paper is decreasing. But there is also the problem that paper has no grease resistance, so if you have a fatty material to pack and it touches the paper, then the grease is permeating through the paper and gives some optical bad spots. So therefore we need to modify the paper by, for example, a coating. And there are several ways to modify a paper. First, the wet chemical coating. Wet chemical coating means we have a liquid lacquer that we apply on the paper by several coating technologies like gravure coating or slot die coating. The other option, which you can see on the right hand side of the slide, is the extrusion coating. That means we liquefy a polymer or a biopolymer and do an extrusion directly on the paper as a substrate. This is from an energetical point of view favored, because you need no curing, no oven in comparison to the wet chemical coating, but there are also limitations, for example the adhesion of the polymer to the paper. And both of the systems, so the wet chemical coating and the extrusion coating, they help us to modify the paper in a way that we increase the barrier, for example, or increase the stability against grease or water. But if the barrier against water vapor is still not good enough by the coating, then we have the option to do a PVD, physical vapor deposition. That means to improve the barriers of the paper, and there is the option to do a coating on paper, and this can be done either by wet chemical coating or by extrusion coating. The wet chemical coating can be done with biopolymers or also with polyolefin-based polymers to increase the barrier against oxygen or water vapor. The extrusion coating, on the other side, can do with the same polymers, but the difference is there is no solvent involved, so there is a direct extrusion of the molten polymer on the paper surface. This is, from an energetically point of view, favored, because you don't need the energy for the oven, but there is some disadvantages on this process. For example, the adhesion of the polymer to the paper. If the barrier you achieve by the coating with the polymers is not enough, for example against oxygen or water vapor, then we can additionally add a physical vapor deposition, which is shown on the middle below. This means you evaporize a material, for example silicium oxide, aluminum oxide or aluminum, and this is building a very thin layer that is has even a better barrier against the gases we were talking about before. Here on this slide you see a summary of the barrier properties that are possible to achieve on paper. You see the OTR value measured at the conditions 23 degrees Celsius and 50% relative humidity, and you see the water vapor transmission values measured at 23 degrees Celsius and 90% relative humidity on the blue box below. So starting from the left side, this is a typical coating with a wet chemical barrier lacquer. Here we are able to achieve oxygen transmission values below 1 or water vapor barriers below 20. If we move from a market available barrier lacquer to a bio-based barrier lacquer, then we can even reach oxygen transmission rates below 10 and water vapor transmission rates below 50. So we are not as good as the market available lacquers, but we have the advantages that we are bio-based and we are biodegradable for some special cases. In the next box you see the option which barrier properties are possible to reach with a so-called nanocomposite barrier lacquer. This barrier lacquer contains silicate platelets that improve the diffusion path for the gases permeating through the system, and this even improves the barrier properties. So we are able to reach here also oxygen transmission rates below 1 and water vapor transmission rates below 20 or even below 10 if we are working with very new silicate platelets that are not market available right now but in development stage. And on the very right hand side you see the barrier values that are possible to achieve with physical vapor deposition. Here both of the gases important for food packaging are below 1, which is a very good alternative for typical polymeric packaging. Talking about the application of barriers on papers, we have two main challenges. First one, the wet chemical coating. As you might know, paper is very rough and has a very high potential to suck some solvents on the surface. So what is happening if you coat paper with a wet chemical barrier lacquer, then the paper is sucking some type of the barrier lacquer, and this leads to the fact that we might have defects if the paper is too rough, for example, or that the whole lacquer is sucked by the paper and there is even no closed layer on the surface. When we are talking about physical vapor deposition, then the whole process of the physical vapor deposition is happening at vacuum, and paper contains some amount of water, and since the water in every paper is different, also the stabilization of the vacuum is not very easy during the process. And if we put the paper into the vacuum and it is dried, then we build up the barrier layer, and after removing the vacuum, the paper is again, because of its hydrophilic nature, taking up some water, leading to an expansion, which is called hydroexpansion, and this might lead to the fact that we increase the number of defects just after removing the paper to a humid environment. Regarding the coating, we already talked about the coating of the paper. There are several coating techniques available for paper, starting from gravure coating to slot die coating or even to comma blade coating. And the amount of lacquer is increasing from left to the right hand side. The importance of the coating technique on paper is shown on this example from a project where we coated 10 grams per square meter PVOH, which is a typical barrier lacquer for oxygen, on an 80 gram paper. And as you can see on the left bar, when we apply the lacquer by K-bar, then it is exactly happening what I talked about before. The complete lacquer is pressed into the paper and we have kind of an immersed paper but not a coated paper, and this leads to a very high barrier value in comparison to a coating with slot die, where we can use either the bead mode or the curtain coat mode, where we really lay a layer of the lacquer on top of the paper, which is not pushed into the paper, and building a closed layer really separated from the paper without any suction of the solvent. And therefore we have much better barrier values on the following two bars to the right. The whole project, which is called B-Party, that's the acronym that we have chosen for the project, is about paper coating and the possibilities for paper coating If you want to have any further information, you're very welcome to scan the QR code. The idea of the project was to coat paper with several water-based lacquer systems, either market-available polyolefin-based or bio-based, and we have built up a whole database for the coating on paper, which was a great benefit for us, and we have shown the dependency of the coating technique on the barrier properties of the paper. On the next slide, we see a more detailed information on the PVD process. Once again, PVD stands for physical vapor deposition. This process is possible to be applied on papers, biopolymers or polyolefin-based polymers, and the result is a 10 to 100 nanometer thick layer of an inorganic layer made of silicon dioxide, aluminum dioxide or aluminum itself. And the challenges we already talked about before are the hygroexpansion of paper and the roughness of paper. On the right hand side you see the interior of the vacuum system that is necessary to apply the PVD process. We start on the right roll, moving the paper below a chill roll. Under the chill roll there is an aluminum target which is evaporized via electron beam. The vapor is crystallizing on the paper surface, and due to the fact that the chill roll is cooled, the aluminum is building a closed and dense layer of aluminum on the paper surface and is then stored on the last roll indicated with a white arrow. So to summarize the whole barrier process on paper, or the single steps, we start with the left diagram where we can show the water vapor barrier on the x-axis and the oxygen barrier on the y-axis. We start on the right top of the value with a paper that is not modified. Then the pre-coating helps us to reduce the oxygen barrier significantly, but there is still some water permeating through the paper. If we do then a PVD coating, then the water vapor barrier is reaching a value around 10. If this value is still not enough for the paper and the application, then there is the possibility to do a top coating, which is protecting the PVD layer, and this top coating is filling any defects and therefore reducing the water vapor barrier to a value below 1. So at each process step we are talking about, you can stop the modification of paper depending on the demand you have for the packed good. One other aspect or one other possibility to apply a very thin coating layer on paper is the transfer metallization. This process is patented by the Fraunhofer IVV and helps to create very good barrier properties on paper by the following process. As said, there are some challenges to do the PVD process on paper, like the hygroexpansion and the roughness, etc. This is neglected by the process that I will introduce now. If you create the PVD layer on a polymeric film, and this is done by coating the polymeric film with a release layer, doing the PVD coating on top of this release layer, and then bonding this polymeric film on paper. And at the last process step, you remove the polymeric film at the release layer, and what you have is a paper that has then adhesive, PVD layer and release layer, and this PVD layer is built up on a polymeric layer, so it had never contact to the hydroexpansion of paper and to the roughness of paper, and is therefore a very good barrier option on paper. Last slide regarding the paper processing in the packaging machines. Paper is a very stiff material, and this causes some challenges by folding the paper. And what you can see on the left hand side is a schematical drawing of a paper packaging during a filling process. First of all, the paper is folded around the shoulder, and then there is a lengthy sealing bead where you can close the paper on the one hand side, and below you have two vertical sealing lines that close the packaging. And this is on polymeric films, no problem at all. If they are thermoplastic, they are sealable. But for paper, you need to introduce also a sealing lacquer, which is in most of the cases the same lacquer that is used for the top coating and the protection. Then I will close with some examples for paper-based packaging, some process or project examples. First, there is a use case in a European project called Flex Function to Sustain. This use case was done together with the company Procter & Gamble, and it's about marine biodegradable shampoo sachets, or generally sachets that are used for cosmetic goods or cleaning agents. Normally those systems are not used in the European market because there we have big packages, but in the third world or for example in Africa or in the Indian market, people tend to use day packages of soaps or washing agents in these daily packages, and these are very small, and the paper is used because it's the only system that is marine biodegradable. We look for a barrier value that is below 5 for dry products and below 1 for wet products, and for a completely marine biodegradable shampoo sachet. The results we gained during this project, first of all, we introduced a nanocomposite barrier lacquer that can provide those properties, so marine biodegradability and the barrier properties, and we also learned as a result the special type of nanocomposite barrier lacquers is only able to be cured with IR curing, and that's the, let's say, the key point of this project. And the benefit of projects like this is that we have a great view on the one of the biggest hygienic product producer in the world, Procter & Gamble, and that we learned really well to work with such biodegradable options. And then I have another project which is a pilot case of the Flex Function to Sustain project. Here we wanted to substitute single-use plastics for fresh foods and vegetables, and this is done by a paper which is kind of transparent, as you can see on the picture. And here, since the time from the creation of the food until the usage of the food is very short, it's not about the barrier against oxygen or water vapor. It's more important to have coating at the inside of the paper which is hydrophobic, that there is no water or no water permeating through the paper, and this we could reach with a market available barrier lacquer against water vapor. And also here we find a very good solution. If you're interested in more information on the two projects, please scan the QR code given on the slides. And as a conclusion, paper is one of the most promising products regarding food packaging because of one point, and this is the recyclability. The recyclability of paper is very much common in Europe. There are big factories who do the paper recyclability, and recycling rates are up to 90%. So if you can manage to create a paper with the specific barrier options on paper, then you really have a chance to get into the market. But there are still some challenges, as mentioned on the slide, with the advantages and disadvantages. Again, for the market opportunities, paper is a great opportunity because it's seen by the customer as a green packaging. And if you have further questions regarding paper packaging, we are very welcome to answer them in the following sessions.